Keyword intro reveal: Damascus steel. In the spring of 1191, a Frankish knight named Roger of Hoverdene wrote a letter from a camp outside the city of Acre on the eastern coast of the Mediterranean. He wrote that the Saracens carried swords of a kind he had not seen before. The blades, he said, were dark, almost black, with a rippling pattern that ran along the steel like the surface of slow water. He said the swords were so sharp that a silk scarf dropped onto the edge would fall in two pieces without slowing. He said the blades did not break, and did not bend, and did not dull. And he said that some of the men under his command had taken these swords from the dead after a fight, and had tried to copy them in the forges of Acre and had failed. He was describing Damascus steel. He did not know how it was made. No European knight in the spring of 1191 knew how it was made. No European smith in the spring of 1191 knew how it was made. And, 600 years later, no one in the world would know how it was made either, because the knowledge of it, the exact, precise, repeatable knowledge of how to fold and forge and quench a blade of Damascus steel, would have vanished. This is the slow story of a metal that was the finest battlefield steel in the world for nearly 1,000 years, and the slow story of how that knowledge was lost twice. Once by accident, once on the page. Settle in. The metal we now call Damascus steel was not originally made in Damascus. It was made in southern India, in a region that the medieval Arab geographers called Hind, in small clay crucibles, in furnaces dug into the red earth of what is today the state of Karnataka and the state of Telangana. The smiths who made it called the metal Wootz. The Arabs called it pulad. The Persians called it fulad. The Europeans, when they first encountered it in the markets of Damascus and Aleppo 6 centuries later, called it after the city where they bought it. The Indian process began with iron ore, magnetite mostly, and some hematite, washed out of the rivers and dried in the sun. The ore was loaded into small clay crucibles, each about the size of a wine bottle. With the ore went a careful measure of charcoal and a handful of green leaves, usually leaves of the bamboo or the cassia plant, and sometimes a small wedge of dried wood. The crucibles were sealed shut with wet clay, stacked in a furnace, and burned for many hours, at a temperature that the smiths judged by the color of the fire alone. Inside each sealed crucible, something specific was happening. The iron was melting, slowly, into a small, dense ingot at the bottom. The carbon from the charcoal and the leaves was dissolving into the iron in a precise and narrow range, between 1.5% and 2% by weight. Below 1%, you get a softer steel. Above 2%, you get cast iron, which is brittle and cannot be forged. Between those two values, in that narrow window, the smiths of southern India had learned, over generations, to land their crucibles every time. When the firing was done, the crucible was broken open and a small steel ingot was lifted out. It was about the size of a hockey puck and weighed perhaps a pound. The ingot was not a finished blade. It was a raw material. It was packed onto a camel with hundreds of others like it and carried north and west. Across the Deccan Plateau, through Persia into Mesopotamia, to the workshops of the great metalworking cities of the Islamic world. The workshops bought these ingots and forged them into swords. The most famous of these workshops were in Damascus and in Aleppo, in what is today Syria. There were others in Isfahan, in Persia. There were others in Toledo, in Spain, after the Muslim conquest of the Iberian Peninsula. But the Damascus blade became the type specimen, the standard against which all other steel was measured. For the same reason, any product becomes a type specimen. Its workshops were the closest to the buyers. Damascus sat on the trade road that ran from Baghdad to the Mediterranean, and from the Mediterranean to every army in Christian Europe. When a knight from Burgundy or Aquitaine wanted the best sword that money could buy in the 11th century, he sent a man to Damascus. And the man came back weeks later with a blade. The Damascus blade had three properties that, taken together, made it the finest battlefield steel in the world, from roughly the year 900 to the year 1600. The first property was hardness. A Damascus blade could be sharpened to an edge that, by the modern measure of the Rockwell C scale, was harder than the European steels of the same period by about 10 points. A typical European sword of the 11th century was forged of pattern-welded iron, soft iron bars folded with harder steel rods, hammered out and quenched. It would hold an edge for a few minutes of fighting before it dulled. A Damascus blade in the same fight would hold its edge for hours. The second property was toughness. A blade can be made very hard, and then it shatters on the first strike. A blade can be made very tough, and then it bends and stays bent. The trick of metallurgy for a sword is to make a blade that is hard at the edge and tough in the spine, that holds an edge but does not snap. Modern smiths achieve this by differential hardening, heating the spine of the blade to a lower temperature than the edge, so that the two parts cool into different microstructures. The Damascus smiths achieved it by something different, by a microstructure inside the steel itself that, when the blade was hammered out from an ingot and quenched in oil, formed bands of softer iron and bands of harder iron, layered together at the scale of microns. The third property, and the one that made the blade famous in the marketplaces of Aleppo and the camps of the Crusaders, was the visible pattern. A Damascus blade, after it was forged and quenched, was polished. And then it was lightly etched with a weak acid, with a neger, sometimes the juice of unripe grapes, sometimes a paste made of clay and lemon. The acid bit into the softer bands of iron in the steel and left the harder bands standing in slight relief. When you held the blade to the light after the etch, you saw a pattern. The pattern looked like the surface of water moving slowly under wind. It looked like the rippled markings of a watered silk. It looked like flames frozen in the metal. Some patterns had names. The smiths called the simplest pattern Qum, which is the Arabic word for sand. They called the wavier pattern Muhammad, after the Prophet. The most elaborate pattern they called Kirk Nardaban, the 40 steps, because the layers were so fine that you could count, in a single inch of blade, 40 individual bands of light and dark. The pattern, for the smith, was a signature. It told the buyer that the blade had been forged correctly. It told the buyer that the steel was real Damascus and not a European imitation. It told the buyer, in effect, that the blade would do what was promised. And the pattern was also something else. It was visible evidence of a microstructure that the smiths did not have the tools to see. The bands of light and dark in the steel were rows of cementite, iron carbide, laid down in regular sheets between bands of ferrite. The cementite is what gave the edge its hardness. The ferrite is what gave the edge its hardness. The smiths who made these blades did not know they were arranging iron carbide into nanoscale layers. They knew only that if you fired the crucible just so, and forged the ingot just so, and quenched the blade just so, the metal came out right. And they passed that knowledge down, master to apprentice, for 700 years. And then they stopped. The European response to Damascus steel, across 5 centuries of the Crusades, and the Reconquista, and the long Mediterranean wars that followed, was a single sustained act of imitation. European smiths tried, from at least the 12th century onward, to reverse engineer the blades they took from the dead and the captured. They could see on the surface of the steel what the pattern looked like. They could measure with a file how hard the metal was. They could feel with a hammer how it rang. What they could not do was reproduce it. The closest the Europeans came was a technique called pattern welding. A pattern welded blade is forged from many thin bars of steel of slightly different compositions, some with more carbon, some with less, that are stacked together, heated white hot, hammered into a single bar, folded over, hammered again, folded again, and so on, sometimes for hundreds of folds. The result is a blade that has on its surface a visible pattern very similar to a Damascus blade. Light and dark bands, wavy lines, rippled markings. But under the microscope, a pattern welded blade is fundamentally different from a Damascus blade. A pattern welded blade is made of layers of different steels welded together at the macroscopic scale. A Damascus blade is made of a single steel that, at the microscopic scale, has organized itself into layers as the metal cooled. They did not perform the same. The Vikings, who fought for centuries against the Muslim armies along the eastern frontier of Europe and into the Caspian, knew this difference well. They made pattern welded blades of their own, and they made very fine ones, and they prized them. But the Vikings also bought Damascus blades when they could, and a Viking grave from the 10th century, excavated in Sweden, often contains a sword whose blade was forged in Aleppo or Damascus, and whose hilt was made in Scandinavia. In the long term, the European answer to Damascus steel was not to copy it. The European answer was to wait it out, to improve, slowly and incrementally, the steels they could make themselves. And, after enough centuries of incremental improvement, to manufacture a steel that, while it did not have the pattern or the romance of a Damascus blade, did the same job. The transition was complete by about the year 1650, with the Solingen blades of the German Rhineland and the Toledo blades of central Spain. By the time of the 30 Years' War, the European sword was, by every metric that a soldier cared about, as good as a Damascus sword. But by then, the Damascus sword was already disappearing. The reason the Damascus blade disappeared is one of the strange small puzzles of the history of technology. Because it did not disappear the way most technologies disappear, gradually, displaced by a better thing. It disappeared abruptly. It disappeared as if the smiths who made it had, in a single generation, forgotten how. The last clearly documented Damascus blades, made by smiths who still understood the full process from ore to ingot to forged sword, were produced sometime in the middle of the 1700s, possibly the 1750s, possibly as late as the 1780s. After that, the blades sold in the markets of Damascus and Aleppo as Damascus steel are imitations, pattern-welded blades, or worse, blades etched to produce a false pattern on the surface of an ordinary steel. The reason for the loss is not perfectly understood. The leading explanation, and probably the correct one, involves the supply chain. That trade route depended on a stable political situation along its length. By the 18th century, the political situation along that length had become unstable in several ways. The Mughal Empire was collapsing. The British East India Company was establishing its hold on the Carnatic coast. The Safavid dynasty in Persia had ended. By the 1750s, the Indian crucibles that had supplied Damascus for centuries were no longer firing. The smiths in southern India, The ones who knew the exact proportion of leaves to ore and the exact color of fire to look for had died, and their apprentices had moved into other work. And the technique, which had always been a craft skill, never written down, passed only by demonstration, was no longer being demonstrated. The Damascus smiths in Syria continued to forge for a while on the ingots they had in stock. When those ingots ran out, they tried to buy more, and there were none. When they tried to make their own ingots, using local Syrian iron and the techniques they remembered from watching the Indian ingots being broken open, they could not. When those ingots ran out, they tried to make their own. The technique of the crucible firing was not in Syria. It had never been in Syria. It had been in Hyderabad and in Mysore, and now it was nowhere. By 1800, the trade in true Damascus blades was over. By 1820, the last smiths who remembered how to forge from the old ingots had died. By 1850, the question of how the original Damascus blades had been made was a curiosity for European metallurgists rather than a living craft tradition. It is one of the few cases in history where the answer to how did they do that was, for a time, completely unknown. In 1819, Michael Faraday, who is now remembered chiefly for his work on electricity and magnetism, published a paper in the Journal of the Royal Institution titled simply Wootz. Faraday was 28 years old. He had not yet done the experimental work that would make him famous. He was a young man working in the chemistry laboratory of the Royal Institution in London, and he had been given a sample of Wootz steel by a Scottish surgeon named Stoddart, who had brought it back from India. Faraday's question in 1819 was the same question that European metallurgists had been asking for 2 centuries. What is in this steel that gives it the property of Damascus? He performed a chemical analysis by the methods of his day and concluded, incorrectly but reasonably for a chemist of 1819, that the special property of Wootz steel came from trace amounts of silica and alumina in the metal. He recommended that European smiths attempting to reproduce Damascus steel add small amounts of silver, platinum, and aluminum oxide to their crucibles. The recommendation was a dead end. Faraday's analytical chemistry was not sensitive enough in 1819 to detect the actual trace elements in Wootz that mattered: vanadium, molybdenum, and chromium, all in concentrations below 0.1%. And he had no way of seeing the microstructure inside the metal, because the metallographic microscope had not yet been invented. Inside the metallographic microscope had not yet been invented. The next serious attempt was made in Russia. In the 1820s and 1830s, a metallurgist named Pavel Petrovich Anosov, working at the Zlatoust ironworks in the Ural Mountains, set out to reproduce Damascus steel by systematic trial. Anosov fired thousands of crucibles. He varied the iron source: Ural magnetite, Caucasian hematite, swamp ore from Karachi. He varied the carbon source: birch charcoal, oak charcoal, dried meat, animal bones, leaves of various plants. He varied the firing temperature. He varied the cooling rate. He kept careful records. In 1837, Anosov produced an ingot of steel that, when forged and etched, showed a watered pattern that European observers agreed was indistinguishable from a Damascus blade. He had produced what he called bulat. He published his method in detail in a paper that ran to several hundred pages. he had not. The blades Anosov made were genuinely excellent. They were probably the best swords made in Europe in the 1830s. They held an edge. They did not break. They had the pattern. But when modern metallurgists in the 20th century sectioned and analyzed a surviving Anosov blade, they found that the microstructure was different from a true Damascus blade. Anosov had produced a steel that was, in modern terminology, a high-carbon hyperrutectoid steel with a watered pattern from pearlite banding. A true Damascus blade has, in addition to that, a particular distribution of cementite carbides on the nanoscale that Anosov's blades do not have. Anosov had reproduced the appearance of Damascus steel. He had not reproduced the steel itself. He died in 1851, believing that he had. And after Anosov, for another 150 years, the matter rested. European and American metallurgists continued, occasionally, to try to reproduce Damascus blades, and they continued, occasionally, to claim success. The microstructure of a true Damascus blade, the one in the museum cases in Istanbul and Tehran and St. Petersburg, the one taken by a crusader from a Saracen at Acre remained into the late 20th century, a thing that could be described but not made. In 2006, a metallurgist at the Technical University of Dresden named Peter Paufler took a small sample from a 17th century Damascus sword, a blade made by the smith Asad Ullah, dated by museum records to approximately 1640, originally housed in the collection of the Bern Historical Museum, and prepared it for examination under a high-resolution transmission. The transmission electron microscope sees down to the atomic scale. It is the instrument that you use when you want to see things that are far smaller than the wavelength of visible light. Paufler was looking for the cementite layers, the carbides that earlier microscopists with weaker instruments had identified as the source of the watered pattern. He found those. They were there. He photographed them. He also found, embedded among the cementite layers, two things that no one had expected. The first was cementite arranged in nanowires, long, thin filaments of iron carbide, only a few atoms across, running through the steel like reinforcing threads. The second was carbon nanotubes, hollow cylinders of pure carbon, the same molecular structure that materials scientists had first synthesized in 1991 and that, in 2006, were one of the most active areas of materials research in the world. There were carbon nanotubes in the steel. Paufler published the finding in the journal Nature in November of 2006. The paper was 3 pages long. The reception was loud. A Damascus blade made by a 17th century Syrian smith, working with crucible ingots from India that had been forged by techniques developed perhaps 1,000 years earlier, contained a class of nanomaterials that modern materials science had only learned to produce in the 1990s. The nanotubes were not, of course, deliberately engineered. The smiths who made the blade did not know that carbon atoms could be persuaded into cylindrical molecular arrangements at high temperature in the presence of certain trace metals. The smiths only knew that their fire had to be a particular color, that their charcoal had to come from particular trees, that their crucibles had to be sealed in a particular way and broken open at a particular time. The nanotubes were a side effect of those choices, an emergent property of a craft tradition that had been refined over 1,200 years, by trial and apprenticeship in the small workshops of Hyderabad and Damascus and Aleppo, by smiths who could not have explained, in the language of modern materials science, what they were doing. The smiths were producing, by intuition and inheritance, a composite nanomaterial. They had no idea that they were doing it. And when the supply chain broke in the 1750s, they did not know that they were losing it either. They knew only that the blades they were forging in the 1750s were not quite as good as the blades they remembered. What Porphyro's microscope showed, in 2006, was that the gap between a Damascus blade of 1640 and a modern European steel of 1980 was not a gap of metallurgy. It was a gap of nanotechnology, 350 years before nanotechnology was understood to exist. The story of Damascus steel is, in one reading, a story about a craft that was almost lost, and then, partially, recovered. The blades cannot be made again exactly the way the 17th century smiths made them, because the Wootz ingots from southern India have not been produced since the 1750s, and the precise composition of the Indian ore from those crucibles is no longer in the ground. But modern smiths can come closer than the 19th century could. There is, in 2026, a small revival of true Damascus forging. Small workshops in India and Russia and the United States, using modern analytical chemistry to back-engineer the original composition, producing blades that are, within the limits of what modern materials science can verify, equivalent to a 1640 Damascus blade. But the larger reading is harder. The reading where the Damascus story is not a story about one steel, but a story about the kind of knowledge that does not survive its own supply chain. We do not know how many other technologies have been lost in the same way. We have the Antikythera mechanism, which suggests that the Hellenistic world produced precision gears that vanished for 1500 years. We have Damascus steel, which suggests that medieval India produced a nanocomposite metal that vanished for 250. We have Roman concrete, which we cannot yet exactly reproduce, because the formula involved a specific volcanic ash and a specific seawater chemistry that we are still working out. We have Greek fire, which the Byzantine navy used to set the wooden ships of Arab fleets on fire from across the water, and whose recipe was a Byzantine state secret that no one wrote down and that we still do not know. In each case, the technology was real. The objects survive. We can examine them. We can describe what they do. We cannot, exactly, make them again. The reason, in each case, is the same. The knowledge of how to make these things was not in books. It was in the bodies of the people who made them, in the angle of the wrist, in the color of the fire, in the smell of the smoke, in the small adjustments that an apprentice learned across a decade of standing next to a master and watching. When the apprentices stopped coming, the knowledge stopped passing. And the knowledge stopped passing. This happens still. It is happening now, in workshops you have never heard of, in the bodies of craftsmen who are very old and whose grandchildren have moved to the cities. Some of what they know will be written down before they die. Most of it will not. That is the small, quiet thought to fall asleep on. There are things we knew as a species that we no longer know. There are things we know right now that our great-grandchildren will not. Sleep well.